So I was asked this afternoon to give a 5-minute presentation on what it is that I do in my research, and since I had take the time to make the presentation, I thought I would share it all with you now. So I don't think it's controversial to say that we depend upon distributed systems in every aspect of modern life. We rely on them in healthcare, in finance, in teaching, in e-commerce, in social media, and in, frankly, just every facet of life. I was having a think when I made this presentation of what distributed systems I had used in the last 24 hours, and this is just a subset of the list that I came up with. So there's many names on here that you'll be familiar with, like Amazon, Gmail, Zoom, Dropbox, GitHub. There's also a lot of names on here that you may not be familiar with. So there's some Cambridge-specific things like Raven, which is the Cambridge University Authentication Service, and Moodle, which is the online virtual learning environment that the university uses. This will be even more true in the future, where we have autonomous vehicles and the Internet of Things and blockchains and electronic voting and all sorts of new distributed systems where our lives will very literally depend on these systems. We expect a lot of these systems. We expect them to be available, we expect them to be there for us when we want them, and we expect them to be correct, we expect them to be consistent, we expect them to behave in the way that we would like them to. However, a quick look in the media tells us that this isn't always true. So here's 3 examples from recently in the UK. The first is an issue with the mobile operators from last week. The second is an issue with some of the major banks in the UK back in January. And the third is this article describing an issue with one of these Internet of Things devices. And I see these issues in my life as well. So on Friday, when it became apparent I was going to be working from home for the foreseeable future because of the coronavirus outbreak, I went online to purchase a monitor. When I started the process, it seemed like there were plenty in stock and everything was going well. I gave my address, I gave my payment information, they took the money from my card, and then at the final step, the process failed. At this point, I've ended up with no product, no computer monitor, but the company has taken my money, and so I was on the phone to them this morning trying to get that resolved. And this is an example of a lack of a property which we call atomicity. And what that means is that when we have a group of operations like this, which we call a transaction, we would ideally like all the operations to go ahead, all the aspects of the process to go ahead, and if not, if it's going to fail, then they should all fail. We shouldn't end up in a state where some of the operations have gone ahead and others haven't. So why is this so hard? There's so many people who are building these systems. Well, mostly because it's a really difficult problem. There's a lot of issues for us to deal with here. Distributed systems are way more complicated than a single server system. We have a high degree of concurrency, for example. We have failures of machines. We have networks which may delay messages, they may drop messages, they may become partitioned entirely. We have machines that may not even be able to accurately tell the time. And the machines, after all of this, may not even do what we tell them. We may give them an algorithm and they may skip certain steps, they may execute it out of order, or they may even be hacked and they may be malicious and they may be deliberately not following the algorithm in order to reach some kind of goal. So how can we fix this mess? Well, as this poster produced by the British government during the Second World War says, systems should keep calm and carry on. In practice, what this means is distributed systems need to embrace failures. Failures need to be included in the design from the very beginning. And this is where my work comes in. My research is in developing novel distributed algorithms which make minimal assumptions about the underlying system while still providing very strong guarantees. So my research bridges the divide between theory and practice of distributed systems. So each algorithm is motivated by a specific practical problem that we're having in distributed systems today. I then design an algorithm and prove properties of this algorithm, and then we feed this back to engineers for them to implement this in practice. As I said, distributed systems are really complicated to reason about, so I don't just rely on my own logic and pen and paper proofs. I make use of formal methods. At the moment, I largely use model checking in a model checker called TLC, which model checks formal specifications written in TLA+, but I'm looking into using even stronger methods, so using proper theorem provers to prove the correctness of these algorithms. So the algorithms that I work on do not assume that, for example, all of the hosts will always be available. They don't assume that all messages will be delivered in a timely manner. And some of the ones I've been working on more recently don't even assume that hosts actually follow the machines actually follow the algorithm that they've been given. So I wanted to dive into one specific example of these algorithms. So the paper I've shown here is called Part-Time Parliament by Leslie Lamport. It's one of the most famous papers in distributed computing. In fact, Leslie Lamport won the Turing Award for his contributions to distributed computing, including this paper that I'm showing here. And this paper is really influential because it solves a real fundamental problem in distributed computing, and that is the problem of distributed consensus. This is the problem of how to decide a single value in a system, which may be asynchronous and where the participants may fail. The algorithm that Leslie proposed is able to solve this problem, however, it suffers terribly with its performance. In particular, to make any decision, at least the majority of machines that are running the algorithm need to agree, need to participate. And that really limits the scale of these kind of systems. So on the right, we have flexible Paxos quorum intersection revisited. So this is a paper of mine, which is probably my most influential, and it revisited the algorithm that was proposed in this paper. The algorithm was called Paxos, that's why this is called flexible Paxos, and it showed that one of its underlying requirements was in fact unnecessary and that the algorithm was conservative. This then allowed us to design many more algorithms for consensus, and in particular ones that don't require this use of majority quorums, thus making them more performant and more useful. And as I said before about taking problems, writing algorithms, and then feeding it back to the engineering community, flexible Paxos is now being used, for example, in Facebook. So, because I'm running low on time, just to quickly summarize, our lives depend on distributed systems, and this is only more and more true in future years. My research looks at how to design novel distributed algorithms that make minimal assumptions, so they're not assuming, for example, that machines will always be up or that networks will always be well behaved, and yet we can formally prove that they provide really strong consistency guarantees. One of these guarantees, for example, is atomicity, which is the issue that I had with purchasing a monitor last week. Thank you, and if you have any questions, please feel free to reach out to me online.